Very good morning, students. Welcome to IIT NEET Foundation or Focus C program by Krishnaveni Talent Schools and the Mastermind Schools. So once again, I welcome all the class 9th students for today's session. As you all can see on the screen, and you are well aware, my subject is physics. We are in class 9th, our ongoing 6th chapter, gravitation. We are today entering into the session number 4. Probably the last but one session. As tomorrow we'll have one more session to close the chapter. And for your reminding, let me remind you a reminder that we have the test 6 exam is on 30th December, right? With same syllabus, entire gravitation chapter. What we started from the session 1 to session 4 or 5, right? Okay. So before going for the what we are learning today, let us recall what we learned earlier 3 sessions, right? Then we'll move to the almost last session of concepts. Okay. So we started this chapter with the Newton under the apple tree, and the apple is fallen down. Then Newton observed that there is a force of earth which is attracting every body towards itself, which is named as gravitational force or simply force of gravity. Then he not stopped there. He continued to study on what factors this gravitational force depends. So from that he proposed one law which is called universal gravitational law or Newton's law of gravitation, which is mathematically given by F is equal to G into M1 M2 by R square. From that he introduced a new word called universal gravitational constant, capital G, whose value is 6.61 into 10 power minus 11 Newton meter square by kg square. That we have seen the derivation also. So G value is constant everywhere and anywhere in the universe. When you go to the earth, when you go to moon, sun, Jupiter, wherever you go, the capital G value remains constant as 6.67 into 10 power minus 11. Right? Correct or not? So we have seen the characteristics of also capital G. So what they observed is the gravitational force between the two bodies mainly it does not be independent of masses. So only depends on the nature of the bodies. Okay. So they are different between we have seen between earth and a body, between sun and earth, between moon and earth, the values can be calculated easily by using the formulas. We have seen how the values changes, the gravitational force values, F, not capital G. Right. When we enter the synopsis 2, we discuss about the acceleration due to gravity, small g. So whenever you are dropping a body from certain height, dropping body not having any velocity, 0. When you are dropping a body with 0 velocity, still it is moving towards the earth and touching the ground with some acceleration. Why? Because of the gravitational force. Such an acceleration produced in a freely falling body due to gravitational pull of the earth is called acceleration due to gravity, small g. The small g value is 9.8 meter per second square on surface of the earth, whereas its value changes from place to place and planet to planet. The value of g value of moon is only 1.67, which is 1/6 of acceleration due to gravity of earth. Whereas On Jupiter, it is 25 meter per second square. On Sun, it is 27.4 meter per second square. The value changes, G small g value. And this value also depends on, even on Earth also, place to place it changes. When you go to the height above from the Earth's surface, the value decreases. Similarly, when you go to depth, also value decreases. We have seen the formulas also. And when you go to some other places, due to change in the atmospheric conditions, there is a slight variation of G value from 9.8 to maybe up to 10 maximum. This variation is due to the local conditions, height, depth. Okay. And same G value is maximum at poles of Earth, whereas 0 on equator. On equator is a minimum. Means when you go from the surface of the Earth to center of the Earth, the value of G becomes 0, 9.8 to 0. That means it is clearly decreasing. Similarly, when it is going up also, at certain height it becomes 0. This clearly indicates that the small g value varies from place to place and planet to planet. Whereas capital G value remains same. Right? So that we have seen already all the how it changes with the depth, how it changes with the height, how it is at equator, at poles. Right? At poles, the value of G is maximum. At equator, value of G is minimum. Then we discussed about even mass and weight. Two important terms which sound same, but there is a big difference between them. There is a big difference. We have seen the difference also like this. Right? So mass is nothing but the quantity of matter contained in a body is called mass. Whereas weight is nothing but it is a force. Weight is a force with which body attracted towards the gravity. Right? So, as you know, the quantity of matter does not change. Suppose you have 1 kg of rice on Earth. When you take that 1 kg of rice to Sun or Moon also, the mass is 1 kg only. But weight changes because weight on Earth is only 9.8, whereas it is on Moon it is 1.67. So due to change in the G value, the weight changes from place to place. Right? So mass is denoted by M and weight is W, and mass is measured by formula mass is equal to volume into density from the definition of density, and weight is measured by mg. W is equal to mass into acceleration. So mass is a base quantity, that is fundamental quantity, and is a scalar quantity because they have only magnitude, no direction. Weight is a derived quantity as well as it is a vector quantity. So SI unit of mass is kilogram, weight is Newton because it's a force only. Mass does not depend on the gravity and is constant everywhere. Mass can never be 0. Whereas weight can be 0 and it is changes from place to place due to change in the gravity. Okay. So mass is measured by common balance. Weight is measured by spring balance, using spring balance. This is the last topic what we learned in the last class, right? About the mass and weight, very, very important. It is helpful for you in your regular syllabus also. Okay. Now we are entering into the synopsis number 3. Okay. Some differently seen here. So what we can see here? Synopsis 3. We can find orbital velocity. Orbit, you know, everybody knows this is orbit. Either Earth is, we all suppose Sun is there. Earth moves around the orbit, or other planets also. They move around the Sun in a specific orbit. Orbit is nothing but path. The path along which body is moving is called orbit. It may be electrons revolving around the nucleus. Suppose it's a nucleus. So electrons are revolving around the nucleus like this. This is called orbit. K, L, M, N. So many you may be knowing, learning chemistry also. Atomic structure, right? So these are the orbits which are around the center. Similarly, there are so many orbits around the Sun where so many planets revolve. 8 planets revolve around the Sun. Clear? That path is called the path followed by the planet. Path followed by the electron. path followed by any object is called orbit. So orbital velocity is nothing but with what velocity body is moving around the orbit. Suppose, example I'll tell. When the satellite is launched, scientists will design the satellite. Okay, they will launch the satellites. While launching the satellite, what they'll calculate is with how much speed this satellite should go so that it can go and fix in a Earth orbit. It should not go away from Earth orbit or it should not come before also. Exactly to go to the Earth orbit, they'll calculate and then they launch. If they won't calculate, it won't be successful. Why some of the launchings are failed? Because of the no plan or there may be miscalculations. Sometimes what happened? Some satellites will escape from the Earth orbit, go somewhere other planets. Sometimes they come back without reaching the Earth also. Why? Because they are not fixed the orbital velocity. Okay. Orbital velocity is not fixed. That formula is this one. Orbital velocity is given by this formula. Gm by r. R plus h means r is the radius of the Earth. How much height we have to say that's h it is. We know g is a gravitational constant, m is the mass of the Earth. So orbital velocity is the horizontal velocity required for object to revolve around the planet. Planet in an orbit is called orbital velocity. Right? Any planet, they want to revolve. For example, see, Earth is revolving around the sun from last 450 million years. The velocity with which Earth is revolving is called orbital velocity of the Earth. Beyond orbital velocity is called escape velocity. Escape. It will go from Earth to some other planet or it may collapse somewhere. So orbital velocity is very important to fix orbit, fix the planet in a specific orbit. You can recently we send the satellite into the moon also. Right, lunar. So they'll calculate how to fix the satellite in the moon orbit because they know the distance from Earth to moon and they arrange the speed, how much speed is required to reach that path, exact location. Then only we'll get the success for the scientist of ISRO or NASA, whatever it may be. Right? So most of you want may become scientists. So this is very much helpful for you to understand the logic. When you are launching or when you want to fix any body on the Earth orbit or any other orbit, so you have to calculate what velocity you have to launch the satellite and how much distance you should cover. According to that, it will launch and will go and fix it in the orbit of any planet, either sun or moon. Okay? Right? That is called orbital velocity. Then, so when you come escape velocity, I told already, other one. Other one is the escape velocity, which is nothing but the velocity. This is the formula, under root of 2gr. It is the minimum velocity with which a body should be projected so that it into space by overcoming the Earth gravitational field. So by overcoming Earth gravitational field, it should go to the space. Such force is called escape velocity. So right, which is given by the formula VE. VG we can call it as VE. You can check the material under root of 2gr. Means it is purely depends on R only, radius. G is constant anyway. A particular planet. Okay. So like this is the formula for the escape velocity. Whereas for orbital velocity, Gm by R plus H under root. By knowing these values, you can calculate the either orbital velocity or even escape velocity also can be reduced like this under root of gr. VO is equal to even under root of gr also. VO. So VO is under root of gr, V is under root of 2gr. Means what is the relation here? V is equal to root 2 times of VO. Then write the relation. Because gr is common, under root of gr is common. Root 2 we have taken like this. This is the relation between orbital velocity and escape velocity. So orbital velocity is the velocity required to fix the satellite or planet into the orbit of a planet. Escape velocity is the minimum velocity required. Minimum velocity. required to overcome the gravitational force. When you are projecting a body, it should overcome the gravitational force, right? That force, that's minimum velocity, is called escape velocity. One is given by formula root TGR, other is given by formula GR, under root of GR. So the relation is escape velocity is equal to under root of, okay, that many times. So before going for the last synopsis, Kepler's law, I will show you one video on this orbital and escape velocity. Just watch the video, then we'll come back to the topic.
Gravitation is orbital velocity. So what is orbital velocity? This is a velocity required by a satellite to put the satellite into its orbit around the Earth. So to solve the expression for orbital velocity, let capital M be the mass of the Earth, capital R be the radius of the Earth, small m means the mass of the satellite, V0 is the orbital velocity of the satellite with which the satellite put into its orbit around the Earth, and here h is the height of the satellite above Earth's surface. So according to the law of gravitation, we know that the force F is equal to capital G, capital M into small m divided by R plus H whole square. So what is R plus H here? R plus H is the orbital radius of the satellite. Here R denotes the radius of the Earth and H is the height of the satellite above the Earth's surface. So we know that for any object or for a satellite to be in a circular motion, there is a requirement of the centripetal force. So the centripetal force required by the satellite to keep it in its orbit is given by F is equal to mv0 square divided by R plus H. We know the formula of the centripetal forces. F is equal to mv square over R. In this case, here velocity V is equal to orbital velocity of the satellite. So we use the symbol V0 square, and for the distance R, here the distance is equal to R plus H. So we replace the R with R plus H.
ज्यादातर वर्किंग प्रोफेशनल्स को मेरी ये बात अच्छी नहीं लगेगी क्योंकि गूगल शीट इस दुनिया का सबसे वर्स्ट टूल है.
To put the satellite into its orbit around the Earth, there is a requirement of the orbital velocity. Orbital velocity make the satellites to move in its orbit around the Earth in a circular path. So hence there is a one force that is required to make the object revolving in a circular path, and that force is a centripetal force. But along with the centripetal force, there is also gravitational pull of the Earth. So in order to make the satellite revolving with the orbital velocity around the Earth, both these forces must be in equilibrium, or we can say that both these forces must be balanced with each other. So for equilibrium, so both the forces are equal to each other, and from this, after solving the equation, we get the equation for V0 square. So V0 square is equal to Gm divided by R plus H. So finally, we get the final result for the orbital velocity, that is a value for the V0 is equal to under root of Gm divided by R plus H. We can also write this equation in the form of the small g, that is when we take into consideration the acceleration due to gravity on the Earth's surface. We know that the value of small g on Earth's surface is equal to capital capital G into capital M divide by R square.
No relation
Here
between capital G and
capital
capital.
M and R is the mass and
You
the
have to replace this
radius of the earth.
in
So
place of
on
M.
rearranging the terms, we get the new equation Gm is equal to small g into R square. Now put the value of the Gm in the previous equation, that is the equation of orbital velocity. After putting this value, we get the new equation for the orbital velocity. That orbital velocity is equal to under root of small g r square divided by r plus h. And on rearranging the
First
terms,
will
we
come
get
outside.
r into under root of g divided by r plus
First
h.
will came out
So
as
this
R.
is the another relation for orbital velocity in terms of acceleration due to gravity on the Earth's surface. Now we are looking next for the special case. Special case when we assume or when this happens, like when satellite revolves close to the surface of the Earth. It means that for this case h is equal to 0. So we can
You can keep
take
0 here.
h is equal to 0 in this equation.
So what becomes
So
R
when
under root
h
of
is
G
equal
by
to
R.
0, we get some another equation. So the another equation is V naught is equal to under root of GR. So this is the equation for the orbital velocity when h is equal to 0, or we can say that when satellite revolves close
you
to
got
the
this one,
surface of the Earth.
R,
So
R,
for the
root R is there. You
value
can
of
write
the
R as
G,
root
we
R
know
into
that
root
the
R.
value of the small g that
The
is
root of G by root R.
9.8 meter per second
You can
square.
cancel root
We
R, root R.
also know
So you
about the
get G
radius of
under
the
root of
earth, that
GR.
is 6.4 into 10 raised
No,
to
no,
power
root
6
R,
meter.
only R can be written as
After
root R into
putting
root R.
these values, we get the result of the orbital velocity in numeric value, that is 7.92
Kilometer per
92
second.
kilometer
That should be the
per
value of
second. There are the
orbital
some
velocity of the
important
Earth.
points that we
Means you have to
understood
launch the
from the
satellite.
equation number 1, and
So you have to launch the satellite with a velocity of 7.92 kilometer per second. Then only the satellite will reach the Earth's orbit. See how much great speed we have to
this one
launch.
is the equation number 1. The first point is from the equation number 1, we can easily see that it is independent of the mass of the satellite. It means that in this equation there is no role of the mass of the satellite. And second, that the orbital velocity of the satellite decreases with increase in the radius of the orbit, and also decreases with increase in the height of the satellite. Because and when if we look at the equation number 1, the r and the h, both these terms are in denominator and they vary inversely with respect to the orbital velocity. So hence orbital velocity get decreases if there is increase in the radius of the orbit and also increase in the height of the satellite. Also the third point, that orbital velocity depends on the mass and the radius of the planet, which is also shown in the equation number 1, that orbital velocity depends upon the capital M, that is the mass of the earth, and capital R, that is the radius of the earth. So this point is also very much clear, that orbital velocity depends on the mass and radius of the planet about which the satellite revolves.
See.
Next topic is a relation between orbital velocity and escape velocity. We know that the escape velocity of a body from the earth is given by relation VE is equal to under root of 2GR. Here the subscript E signifies escape velocity, and the orbital velocity of the satellite revolving close to the earth's surface is given by V naught is equal to under root of GR. Divide both the terms, and after this we get the answer that is equal to under root 2. Cross multiply these terms, we get the answer of the escape velocity in terms of the
Two times
orbital
of orbital velocity.
that is VE is equal to under root of 2V naught. So hence we can say that escape velocity of a body from the Earth's surface is under root 2 times its velocity in a circular orbit just above the Earth's surface.
Hello to all wonderful teachers
Got
out
that?
there.
Clear.
This video is
Just a
for
minute.
you. As a teacher, you can earn up to 20k to 50.
So the next topic is time period of satellite. It means that
So anyway, it is
time
not there for us. We'll see in the next class. So one more video is there about our next topic, Kepler's laws. Small video on Kepler's laws of
Hello learners, this is Easy Engineering. Today we're going to talk about another fun topic in physics. It is all about the Kepler's laws of planetary motion. Kepler's laws of planetary motion are laws describing the motions of the planets in the solar system. They were derived by the German astronomer.
how the Newton's laws of motion is there in planetary. While studying about the planetary system, Kepler proposed the laws under Kepler's law of
Johannes
motion.
Kepler. There are
Laws
three
are
laws of planetary motion. Let us talk about them
So
one by
Johannes
one.
Kepler.
Kepler's first law of planetary motion, sometimes referred to as the laws of ellipsis, can be stated as all planets move about the sun in elliptical orbits.
First point is this. It is also called as law of ellipse. Elliptical shape. Egg.
Having the sun as one of the foci. This means that planets are orbiting the sun in a path described as an ellipse. This is a picture of an ellipse. Suppose this ellipse is where the planet Earth moves. The Earth moves along the ellipse around the sun. The sun is located at either one of foci of the ellipse. Now let us move on to the second law. Kepler's second law of planetary motion, sometimes referred to as the law of equal areas, can be stated as a radius vector joining any planet to the sun sweeps out equal areas in equal lengths of time. The second law describes the speed at which any given planet will move while orbiting the sun. Note that when a planet is close to the sun, it moves fast, but when a planet is far from the sun, it moves slowly. So if we draw an imaginary line of the movement of the planet and the sun for every month of the year, we can see that when the planet is close to the sun, it will form a wide but short triangle. And when the planet is far from the sun, it will form a thin but long triangle. The Earth would have to adjust its movements in order to match the imaginary area. Did you know that the knowledge of Kepler's second law has proved the importance of Newton's law of gravitation? Newton showed that the motion of bodies subject to central gravitational
Newton and Kepler. So by using the Newton's law of gravitation, Kepler proposes the three laws.
force does not always follow the elliptical orbits as specified by the first law of Kepler, but instead, planets or other heavenly bodies can take paths defined by other open conic curves. Amazing, right? Now let us move on to the Kepler's planetary motion, sometimes referred to as the law of harmonies, can be stated as
Of time period also.
the squares of the sidereal periods of the planets are directly proportional to the cubes of their mean distances from the sun. It compares the orbital period and radius of orbit of a planet to those of other planets. It is the ratio of the squares of the periods to the cubes of their average distances from the sun is the same for every one of the planets. The comparison of each planet can be shown in this illustration. Now, what does that mean? Kepler's third law means how long a planet takes to go around the sun, which is its period, is related to the planet's mean distance from the sun. That is, the square of the period divided by the cube of the mean distance is equal to a constant. And for every planet, no matter what its period or distance, t squared over r cubed is the same number. And that's it. Did you enjoy our topic for today? I hope you certainly did.
Right. So these are the 3 laws of Kepler, which is our next explanation part, that is in synopsis 4. Okay. So what they are saying, clearly explained that there are 3 laws are there for Kepler. So in first video, we discussed about what is the orbital velocity and what is the escape velocity. Orbital velocity is nothing but the velocity with which a satellite revolves in a specific orbit, right? Or a satellite is launched to fix it in a specific orbit of a planet. And whereas that is given by V is equal to under root of 2gr. Whereas escape velocity is nothing but the minimum velocity with which an object is launched so that it overcomes the gravitational force and reaches the space. Okay, that is given by V is equal to under root of gr. From that we got that velocity, escape velocity is equal to under root of 2 orbital velocity, the relation between these two. Okay, then we'll come across the synopsis 4. You can see on the screen the 4th synopsis or last synopsis. So that is Kepler's law of planetary motion. So this is purely making use of the Newton's universal gravitational law. Kepler proposed 3 laws. 3 laws which are called, popularly known as Kepler's laws of planetary motion. Laws of planetary motion. The 3 laws which are shown in the video, right? So what is the 3 laws? Just let me show you. Or we are explaining with one example, but I'll explain it to you. So first class, then Kepler's first law says that Kepler's laws. So first law is called law of orbit. Law of an orbit. Second law is called law of area. Third law is called law of time period. Means this is purely related to planets only. Whenever planets are revolving around the sun, they follows the 3 laws. So one first law says that suppose, so Earth revolves around the sun in the not perfect circle, elliptical. Say elliptical orbit will have 2 focus. Generally circle will have only 1 center, but ellipse will have 2 foci, they are called. One focus, one focus. It may be either here or here, right? Say F1 or F2. So sun may be either here or here, no matter. But Earth revolves around the sun, right? At sun has one of its foci. Sun may be either here or here, depends. We cannot say because it's elliptical shape. There won't be not a single center. Circle means only one center is there. But elliptical, there are 2 foci. That is the first law says. That's why it's called law of orbit. The law of area, whenever the Earth is moving, it covers equal areas in equal interval of times. Even though the distance from the Earth to Sun changing, area covered, whenever it is very close to the Sun, it moves very fast. Whenever it is away from the Sun, it will move very slow. But overall, the area covered is same. That's why it's called law of area. And third one is law of time period. Time period is nothing but time taken to complete one revolution. 1 day. For example, Earth complete 1 day, it covers the Sun. Example. It's a time period of Earth. So it is not same for all the planets. So as per that, they given T square is directly proportional to R cube. So sir, T cube is directly proportional to R square something. The relation between time period and radius of the planet. So radius of the planet is not same because Earth may be close to the Sun when compared to the Jupiter or Mars. Changes. As the radius changes, automatically time period changes, automatically the law of time period changes. So all these 3 laws together called Kepler's laws of planetary motion. Okay, clear? So we almost completed the topic here chapter. We have some solved example. If possible, tomorrow we'll discuss about the solved examples and worksheet. Now, you can see on the screen the home task, homework. Differentiate between escape and orbital velocity. Okay, escape velocity and orbital velocity. That is VE and VO. You can write the definition, you can have the relation also. VE is equal to under root of 2 VO. Right? Copy the question in the notebook and write the answer in notebook. So that's all for today. Thank you very much, students. Have a wonderful day. Thank you.